we get started on our second lecture. It seems that some people are having trouble connecting, so the internet, maybe the heat wave is causing internet or power kind of difficulties, but we'll live with it. What we want to do is go back to the lecture that we started last time, and in that case, we go and share our website here. And we need to digress on one interesting aspect. Instead of going directly to the first chapter that we started last time, we are going to digress and access the data files, or the data warehouse in the terminology of information technology, and learn how to access the data. In that case, it's named data mining. So the databases that we use are listed on our web page in the external links, nuclear data for the isotopes and elements. And we all have learned already about in chemistry classes about the periodic table of the elements. This is the one that you can access from the Los Alamos National Laboratory. And if you look at the periodic table of the elements, you'll find that there are two boxes here. The first one is a whole long series of elements starting with lanthanum. So we call it the lanthanum series, or the Lanthanide series. The second one also is a whole set of elements that we call the actinide series, because it starts with the element actinium. The Lanthanide series is also described as the rare earth elements. It contains elements like lanthanum, cerium, promethium, neodymium, prometheium, and so on. And these are the elements that are needed in our new technology of implementing renewable sources of energy. For instance, neodymium in particular, if you find neodymium here, Nd is used in making magnets for wind turbines, for electrical vehicles that are much, much stronger than the iron cobalt electromagnets that are used commonly. The other series, which is the actinides, starts with the element actinium, but it contains the elements of interest in our class here. The most important one is obviously uranium. The atomic number of uranium is 92, meaning that it contains 92 electrons and 92 protons for the charge neutrality of the atom. And its mass number is 238, meaning that the number of nucleons, the protons and the neutrons add up to 238. Now, this is one single isotope of uranium, 238. You'll find that we have other isotopes like 235, 234 that occur in nature. Notice that the actinide series also contain elements that we are going to deal with, particularly plutonium. Plutonium is named after Pluto, one of the planets, and it's basically being discussed whether it's a planetary body or a planet. Let's call it a planet for now. But other elements like thorium, protoactinium, neptunium, americium, curium, berkelium, californium, einsteinium, fermiums, mendelevium, nobelium, and this is lawrencium, I think. And they keep discovering more elements, but our concern is going to be uranium, thorium, protoactinium, neptunium, and plutonium. The information in the periodic table of the elements, also called the Mendeleev table, is not sufficient for us to deal with the nuclear structure of the atom. It deals primarily with the atomic structure. Notice, of course, that column number 1 are the metals, elements that contain a single electron in their outer layer: lithium, sodium, potassium, rubidium, cesium, francium, and interestingly enough, hydrogen is considered as a metal. In the core of the largest planet, Jupiter, hydrogen is so much compressed that it acts almost like metal there. The last column, of course, is the noble gases like helium, neon, argon, krypton, xenon, radon, and I don't remember this one, orgnium, I think. I'm not sure it's a new element. So this is the electronic structure, the number of electrons in the outer layers. And we divide the periodic table of the elements into some naming from when the elements were first discovered. However, to get information about the nuclei, we have to go to what we call the chart of the nuclides, or the table of the nuclides. There are many issues of it, from the Brookhaven National Laboratory, for instance, in Japan, in the United States. In Japan, they have their own chart, Japan Atomic Energy Authority. In Germany, they have the Universal Nuclides chart. I like the one from the Korean Atomic Energy Research Institute. So let's go to the chart of the nuclides from at Carey, because they maintain it really well. And in fact, the previous versions here are the best of them, easy to use. If you look at the table of the nuclides, or the chart of the nuclides, you'll find that we have a plot of the number of protons, or the Z number of the isotope, the atomic number of the isotope, against the number of neutrons in the isotope. You notice that this is a bunch of about 1,000 squares here. The blue one represent elements that occur in nature. They may be radioactive or not radioactive. But then on that side of the blue line here, which is a stability line for the nuclides in nature, you'll find that there are many other isotopes of these elements. And when you come to the right side, obviously, you have a larger number of neutrons in the nucleus than the number of protons. Notice here that if n is equal to z, n is the number of neutrons on the x-axis, z is the number of protons on the y-axis. You find that in nature, nature favors a larger number of neutrons than the number of protons. If you go as n is equal to z, you get some kind of line that has a slope of 45 degrees. It turns out that the isotopes, in that case, that contain a large number of neutrons, tend to try to reach a stability line by emitting a negative electron. We'll study that in more detail in the chapter on radioactivity. So radioactivity is the way that isotopes try to reach that stability position right here. If they are above the stability line, the blue line here, all those squares contain also isotopes, primarily invented or created by man. Only the blue lines are the ones that occur in nature. All the others here, more of them than exist in nature, are man created. How do we create them? By the modern day alchemy of the transmutations of the isotopes. You absorb a neutron in a nuclear reactor or in a particle accelerator, or actually also some of the isotopes are produced in nuclear detonations or nuclear weapons. If you are above the line of stability, you have an excess number of protons. Again, the isotopes try to reach stability by, in that case, instead of emitting a negative electron, they emit the antimatter of the negative electron, which we call the positron. So it's a particle that has the mass of the electron, but in that case, it is positive in charge. Or they try to reach stability also by reducing the number of protons by absorbing an inner electron from the inner electron shell. We call that electron capture. Let's see how we can use a chart of the nuclides and to access data about the radioisotopes and elements. If you click on it, you'll find again here more detail about the blue squares. These are elements at random here that exist in nature. You go below it, you get all those different other isotopes that are created by humans. These are the ones that have a larger number of neutrons than protons, and they emit beta particles, negative beta particles on top. These are isotopes that have an excess number of protons, so they emit positrons, the antimatter of the electron, or decay by what's called electron capture. The element, the nuclide that we consider that is of most interest to us is uranium. So if you go there to the nuclide, uranium, you enter uranium, then press enter. It gives us information about uranium. 92 means it has 92 electrons, as we know, but it gives us information about the isotopes of uranium. You see here that in nature, naturally occurring isotopes, we have 3 isotopes: uranium-234, uranium-235, and uranium-238. In parentheses here, you find the abundance of the different isotopes in atomic percent, how much the percentage of atoms of that isotope occur in nature. You observe here that 99.2745% of uranium occurs as the isotope uranium-238. A very small amount, uranium-235, 0.72%, also occurs in nature, and the smaller even amount of uranium-234. It turns out, as we'll study, that the isotope that produces fission power for us is primarily uranium-235, not the uranium-238 isotope, as we started to learn in the first chapter about the birth of the nuclear age. There are other isotopes that are created by humans in that case that do not occur in nature, a larger number, as you could see here, than the one that occur in nature. Suppose I want to learn more about the isotopes, so I can click obviously on the link for uranium-238 here, and it will give me more information. One of the important pieces of information here is that it has a mass number of 238.050. We are going to continue using the atomic mass unit, even though there is a tendency to change it by a new unit because it's really available to us in the databases, plus or minus, because this is the error in the measurement. These masses in atomic mass units, we'll define it as we go along, relative to the mass of the carbon-12 isotope that is considered as exactly 12. It gives us information about the abundance. We said already 99.274%. And then it gives us information later on about the mode by which it emits radiation. Alpha decay, as you know, is the emission of a helium nucleus with a half-life of 4 billion years. So from the time of the creation of our Earth in a monumental phenomenon of explosion of a star, a supernova, this uranium is still existing today. Let's go back to the other isotope of interest to us, which would be uranium-235. Yes?
Your video is off.
Excuse me?
Your video is not turned on.
What is not done?
Your video.
Oh, no. Okay, so let's... is that now working?
Yeah, now it's working.
Yeah, it turned itself off. I'm sorry, but
no, it's okay.
I think we still can continue sharing the screen here. I hope I haven't lost it. We are talking here now about uranium-235. Thank you for your observation. You notice that its atomic number is 235 atomic mass units, and its natural abundance is much, much less than the abundance of the uranium-238. It's 0.72%. It's about 1 in 140, meaning that out of 140 atoms of uranium-238, we have only 1 atom of uranium-235. Yet, uranium-235 is the isotope that can fission with those thermal neutrons that we mentioned last time. Neutrons are born from fission with an energy, a kinetic energy of 2 million electron volt. We use a moderator. In that case, in the Chicago pile number 1, as we described it, it was graphite or primarily carbon-12. All right, so we can go there and learn more about carbon then as a moderator. So this is C here, and we press enter, we get information about carbon. Carbon is two isotopes in nature, carbon-12, 98.89% in atomic percentage. This is the number of percent of atoms of carbon-12, and there is the carbon-13 isotope, only 1.11%. All the other isotopes here are artificial isotopes or created that are not created directly in nature. In particular, the carbon-14 will be of interest to us because it is used in what's called carbon dating. You can estimate the age of archaeological samples by studying the details of how that carbon-14 decays, and it is formed by the interaction of cosmic rays by generating neutrons in the Earth's atmosphere. Other elements of interest to us are going to be maybe lead, beryllium, and of course water. So in that case, we think about hydrogen. So let's look at the hydrogen isotopes. You notice that hydrogen is primarily the isotope H1, the most common isotope or element in nature is hydrogen, obviously. The hydrogen one is 99.98% in nature, but we have a form of hydrogen where there is an extra neutron. We call it the deuterium. So that's represented as H2. Sometimes it's represented as G2. Very little of it exists in nature in all the water on Earth, and it's of great interest in future fusion reactors, because if we extract it from water, we can generate energy through the process of fusion instead of the process of fission of uranium-235. One isotope that very rarely occurs in nature is an isotope of hydrogen that contains two extra neutrons, one proton and two extra neutrons. It's represented as H3. It's also called tritium. And here is the tritium. As you could see, it is radioactive. It has a half-life of 12.3 years. It emits a negative electron to a stable isotope helium-3. We'll detail that as we go along in more detail and use a chart of the nuclides if we want to study nuclear phenomena in general. All right, along this line, we can go back to our first chapter and get a better understanding of what went on when people started in the period of time where the first reactor was built, as we are trying to cover in our chapter on the first human-made reactor. We stopped at the point where we were looking at the different milestones that were reached just before we had the privilege here in Chicago, Illinois, where the first reactor was built and successfully operated by Enrico Fermi. It says that low system resources may affect your audio quality. Try closing some applications to improve performance. I cannot do that, so let's try to live with it. In the worst situation, you read the lecture notes, answer the questions, and we can proceed from there to make it a true internet kind of a connection. So that was the Chicago Pi number 1. You notice the graphite here with the balls of uranium that Enrico Fermi shown here. These are the balls of uranium built layer upon layer until they reach what we are going to be calling a critical mass, and that was the power producing part of the whole system. I suggested that this did not occur out of thin air. There were scientific milestones that were reached earlier, and you may have read about them in other classes, like in modern physics, for instance. But the main milestones were the discovery first of radioactivity. And it was discovered in France around 1896 by Henri Becquerel. That's the name of the person who discovered radioactivity. To honor him, we are going to use his name for a unit of measuring activity, how much radioactive isotopes emits radiation as a function of time. This was followed by two pioneers, Marie Curie and Pierre Curie. They were a husband and wife couple, and they discovered, they studied the ores of uranium, and they made a fascinating discovery. Marie Curie is renowned for the discovery of two elements, not just one element, but two. She discovered the element radium in the ores of uranium, and later on that she discovered another element. Since she lived in France, married to Pierre Curie, but her native country was Poland, so she named it polonium. So polonium is named after Poland by Marie Curie. That came in only 2 years after the discovery of radioactivity by Henri Becquerel in France. You'll find that the Curie unit is also used intermittently with the Becquerel unit for the measurement of activity or the radioactivity of the elements. Their work was a result of earlier discoveries in 1890s, an earlier discovery in 1897 by J.J. Thomson in the UK, who carried experiments with cathode ray tubes, and after the discovery of X-rays by Röntgen in general. Came in 1905, and Albert Einstein theoretically established the equivalence of mass to energy, the very famous equation E is equal to delta mc square. The ideas came up very quickly that with the equivalence of mass and energy, you can transform mass into energy if you can fission the nuclei of the elements. In that case, the element that is very easily fissionable is uranium-235. And that came after James Chadwick in the UK again had discovered the neutron in 1932. And in that case, Enrico Fermi, Irene and Frédéric Joliot-Curie, these are the children of the Pierre and Marie Curie couple. They also got themselves into the field of nuclear science in the 1930s. And then came Enrico Fermi in Italy, started conducting experiments on the interaction of neutrons discovered by James Chadwick on piles of uranium. As I suggested, the winds of war were blowing in Europe, so Mr. Enrico Fermi came to the United States, to the University of Chicago, and started conducting experiments on neutrons' interaction with materials. Came in two chemists, Otto Hahn and Fritz Strassmann in Germany, and they started bombarding uranium with those neutrons that Mr. Chadwick had discovered. And then they discovered in the products of the bombardment elements that are in the middle of the periodic table, like barium. They couldn't explain it, but they had one of their students that also has left Germany sensing the winds of war, and that was a young lady, Lise Meitner, at the time. She had migrated to the UK, and she explained to Otto Hahn and Fritz Strassmann, with whom she worked earlier, that it could be the process of fission. And she used a very simple model of the fissioning of uranium-235 into two particles that have now a positive charge. She calculated the Coulomb repulsion energy between the two and came up that that process of fissioning of the nuclei can produce a tremendously large amount of energy in the million electron volts of energy. she communicated her information, that is Lise Meitner, to people in the United States, in Norway, and the UK, Rutherford, for instance. And the idea came up immediately by Lise Meitner that the discovery of fission in Germany, in that case, can be used for the development of some kind of a very important weapon. And they worried with the winds of war in Europe that Germany would use it for producing a weapon against the allies, the other Western states. Came in a gentleman, Mr. Shown here, Leo Szilard from Hungary, and he convinced Albert Einstein, in that case, to write a letter. They're reenacting that process here. They sent it to, at the time, here in the United States, President Franklin Roosevelt in 1939. And they basically suggested that Germany, with the discovery of fission in Germany, could end up producing a weapon that is of great concern to the other European powers. As a result, President Franklin Roosevelt started a committee. They called it the Army Manhattan Engineer District Project. In short, the Manhattan Project in the United States, to try to study that process so that Germany would not monopolize the production of a weapon from the fissioning of uranium. The British also had their own group or committee. They called it the Military Application of Uranium Disintegration, the MOD type of project. As a result of that project, work was initiated at the University of Chicago Metallurgical Laboratory under another scientist, Arthur Compton, in 1942. And the culmination of all these discoveries and effort was the building and operation of the Chicago Pile #1 that we described earlier. Here we go through a very simple kind of analogies that may have been missed in other textbooks. Is that the Einstein equation obviously suggests that if you take the mass of any material, you multiply it by the square of the speed of light, you have units of energy. So that implies that mass can be converted into energy. It also can imply that energy can be converted into mass. You see, the equality sign does not go only in one direction. In fact, something interesting is that if you have a mass, the energy content of the mass is described by our very famous Einstein equation. E sub m is equal to mc squared. But when you have radiation, like gamma rays or X-rays or just plain light, the energy, we don't have a mass anymore. It's electromagnetic radiation. And the energy of electromagnetic radiation is described as h nu, where nu is the frequency of the radiation, which is also equal to the speed of light divided into the wavelengths. And with the constant of nature here, h is what we call the Planck's constant. So if you take the mass here and the energy of the mass equated to the energy of the radiation, you have mc squared for the energy in a mass. You equate it to the energy in radiation, and you find something very interesting here, that mass can be equivalent to the existence of radiation with a proportionality constant of h, Planck's constant, divided into c squared. If you have a high temperature also, we have a thermodynamic relation that equates the temperature of any object in Kelvin. So down right here in thermodynamics, capital T, we mean the kelvins or Kelvin degrees, which is 273 plus degrees Celsius. And we have another constant of nature here, which would be the K, the Boltzmann constant. If you equate the three equations for the mass, the to the MC square equation of Mr. Einstein equation to the mass of an object at a very high temperature, you find that the mass can also be equivalent to the temperature in general. So another alternative is that if you have radiation, is that in radiation we have the Stephen Boltzmann constant here that tells us that the energy in radiation is proportional to the force power of the Kelvin degree. So another equation for mass can be written not just E is equal to mc squared. You find that the mass can exist if we have very, 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 very high temperatures like happens in the stars in general. So these are equivalences that we'd like to keep in mind. One interesting implication for it is will be discussed later in what we talk about as the major part of the mass of the universe is what we call black matter and black energy. And it doesn't have to be mass. In fact, this equation right here suggests that if you have electromagnetic radiation that has a very, very, very high frequency, it can be turned into mass. There is an equivalent between the two. The mass here is proportional to the frequency of the radiation. This is a tentative explanation for the existence of black matter and dark energy in general. Coming back to the practical applications away from theory, as I suggested, in the United States, as a result of the letter by Leo Szilard and Einstein to President Roosevelt, is the starting of the Manhattan Project. The Chicago Pi #1 was dismantled, rebuilt on a larger scale at what is today called the Fermi Laboratory or Fermi Lab around that still exists today as in around Chicago, and they named it Chicago Pi #2. But the most important thing is now that the United States embarked into the Manhattan Project. Many of the scientists in Europe, particularly from Germany, Hungary, France, and so on, were invited, Enrico Fermi were invited to the United States, and the leadership to carry out the Manhattan Project was given to General Leslie Grove, shown here. He was a civil engineer, so the whole Manhattan Project was carried by a civil engineer, and he had made his name building the Pentagon building, as you know, in Washington, DC. He was a good engineer, but he needed input from the scientists. He found himself a scientist that he went along with, shown here. That is Robert Oppenheimer, a scientist from the University of California at Berkeley. And they started setting together a scientific project that was called the Manhattan Project. Mr. Robert Oppenheimer used to go horseback riding to an area of New Mexico, which is today the site of a national laboratory, the Los Alamos National Laboratory, as a way of studying how to use fission as a way of preempting what the Germans were thought to be embarking on in creating a weapon of war. The Chicago Pi #1 and Chicago Pi #2 were not good enough in terms of their ability to produce fissile fuel. I'm sorry, here I have to turn this off. So another reactor had to be built that had a greater power, and this was designated as the X1 reactor, shown here. It was a large pile of graphite with lots of tubes going through it, where uranium was introduced from one side. A chain reaction was initiated, and the chain reaction produced neutrons that were absorbed in the more common isotope of uranium, in that case, uranium-238. As a result, it produced another element in the actinide series, we'll look at the equations for that process in the chapter on nuclear transmutations, and that is plutonium, particularly the isotope plutonium-239. So that was one way of producing an isotope other than uranium-235 that can fission practically with very low energy neutrons. Zero energy neutrons can fission uranium-235 as well as uranium-235. Why was that? Because it's easier to separate the plutonium from uranium with a chemical process. There are different elements, so chemistry can isolate plutonium, which has a mass number of 94, an atomic number of 94 electrons, from uranium, which has only 92 electrons. However, still the emphasis has been on uranium-235, but the question is how to separate the uranium-235 from the uranium. Both of them have 92 electrons, so chemistry-wise, you cannot separate them. You needed a physical process. We'll deal with this in a moment, but that graphite reactor, or the X10 pile, was built in what is today another national laboratory in the United States. That's the Oak Ridge National Laboratory. The power of the Chicago pile number 1 from 1/2 of a watt has been increased in that case to the level of the 20 million watts. The reactor was air-cooled, and lumps of uranium were introduced from one side. You add another lump, you push it to the other side, and that is the patent application for part of the patent application for that reactor. Then the lumps would fall from the other side into buckets of containing water, and then using chemical processes, you would separate the plutonium from that uranium material that you have irradiated in the reactor. So now we have two processes by which we can produce the fissile isotope, an isotope, either plutonium-239 or uranium-235, that can fission with zero energy neutrons. Along this line, they needed to build even larger reactors than the X10 reactor at Oak Ridge National Lab. And if you build a nuclear reactor, you produce a tremendous amount of heat, and you have to reject that heat. The 1/2 watt of the Chicago pile number 1, it's a thermal watt, it was heat, had to be raised to the level of 250 million watts to produce significant amounts of the isotope plutonium-239. So they built 9 reactors, 9, not just 1 or 2, 9 reactors along the shores of the Columbia River in the state of Washington. That's where the Columbia River is present, to take advantage of its cooling properties. And those reactors' job was to produce that isotope plutonium-239. I'll send you to the chart of the nuclides as an assignment to practice extracting information about the nuclei and the isotopes. These are pictures of those reactors that were built to produce that plutonium. Site W in the state of Washington. You could see here, this is the Columbia River. It's a desert area, but the river passes there. And as I said, they built 9 reactors. Some of them are shown here. They were designated as A, B, C, D, E, and so on. This would be, again, the Columbia River shown here. There are different pictures shown of those reactors. With the reactors, I had to build processing plants where chemistry is conducted on the fuel of uranium-238 mixed with uranium-235 that now turns the uranium-238 into plutonium-239. Notice something interesting here is that uranium-235 is an odd number, mass numbered isotope. 235, 5 is an odd number. 239, the isotope 239, plutonium-239 is also an odd number. And these isotopes in nature are very unstable if you hit them with a neutron. Not so for the uranium-238 isotope. So in that case, we call them fissile elements. Those reactors now are not in operation. They're too old to, to operate in a safety way, but they left one of them as a basically a historical monument surrounded by a fence, and you could see the Columbia River in the background. Pictures taken on the inside of those reactors when they were built can give us an idea about their size. They're quite large in size. These are the tubes. The graphite would be built here in the center. The tubes where the uranium would be introduced from one side and extracted from the other side are shown. They started there with developing the ideas of clean rooms, because any isotopes, like if you introduce any boron to the structure, it would absorb neutrons and you cannot basically start the chain reaction. So this is the C reactor at the site of Hanford in Washington. Notice that the Chicago Pi #1 with a ½ watt of power did not need any cooling. The X10 reactor needed air cooling. This reactor at Washington needed water cooling because of the tremendous amount of heat they produce. In the end, the face of the reactor looked with horizontal tubes shown here, This is the N graphite moderated and water-cooled reactor. You could see it's the same shape as the X10 reactor, but producing much greater power. And this is in fact a picture of another one of those reactors. That's a K reactor. Notice the size of it. This gentleman there standing in front of it, and a bridge basically that rises up and down, adding fuel from one face of the reactor and then extracting it from the other face. This is a detail about those tubes that are shown in that reactor here on the front, where water now is introduced and cooling the reactor, and then uranium slugs were introduced from one side to the other. You could see here the water flowing from one of those tubes. The fuel itself would be irradiated, plutonium produced in it. You can store it underwater. Water is a very good shield against radiation. This is a shape of that fuel that was used in the N reactor. I showed the picture from the different reactors. Now you had the mixture of plutonium-239 that we mentioned earlier with the uranium-238 and uranium-235, and you needed to extract that plutonium from the uranium fuel. The radiation levels in that case were quite high, so they had to do all the work of extracting the plutonium from the plutonium on a remote control basis. So they did that in what they called canyons, basically chemical reprocessing plants. The thickness of that concrete here was 15 feet, and they had to develop the techniques for remote imaging using periscopes initially, and then they used the video cameras. So the invention of the video cameras was built when they built those canyons. I call them canyons because they were so large and so huge, and everything had to be done with remote control methods because of the very high levels of radioactivity. This is a picture taken of the inside of one of those reprocessing plants. If you look carefully here, this is a processing vessel. It was a very large industrial process given to the chemical company that was renowned at the time, the DuPont company. And the DuPont company, and for on a cost plus basis, basically the DuPont company accepted $1, just $1 from the government, plus all the costs that they incurred in carrying out the chemical, developing the chemical processes. And what they did is that they learned the technology and developed it for other purposes. But look at the nightmare in terms of tubing that had to be connected together and operated on a remote control basis, extracting the plutonium from the uranium. This is another overhead view with the cameras, of course, not direct eye view because the radiation levels would be excessive. They had a control room that in the reprocessing plant at the Canyon F control room. All right, we said that the effort tried to produce a plutonium-239 isotope that is fissile, that can fission with zero energy neutrons. But there was another effort, since they didn't know which isotope would do the job, of separating uranium-235 from uranium. Notice that we said that uranium-235 is 100 in 140 or 0.72% of uranium in nature. 235 and 238 uranium have both the same atomic number, the same number of electrons. So they're hard. You cannot separate them chemically. So you needed a physical process. In that case, they used electromagnetic separation. We'll have a whole chapter on the separation techniques later on. So they built electromagnetic separation units. One was called the alpha racetrack or the Calitron. Calitron stands for California cyclotron. It was a cyclotron device where if you inject a charged particle in a magnetic field, the charged particle rotates around the magnetic field line. Whereas if you inject it into an electric field, the charged particle moves along in the same direction as the electric field lines. So they use those magnets here to generate different radii of curvature of the rotation of the isotopes 235 and 238 of uranium inside the magnetic fields, and in that case collect them and separate them from each other according to what's called the Lorentz equation. We'll describe that in more detail later on. This structure here produced only gram quantities for studies. It was not enough, so they supplemented it with another track, racetrack, they called them. That is the alpha 1 track, and that's a beta track on the right. And in that case, they had to use tremendous amounts of electricity. That's why they built it at Oak Ridge, Tennessee. Oak Ridge, Tennessee gets its power from the Tennessee Valley Authority today, which is a government agency with a huge supply of hydroelectric power for the electrical processes for the Department of Energy, as well as coal power, electrical power generation. Those two processes produce only gram quantities, but General Leslie Grove of the uranium-235 kept the process going to mislead the Russians. In his memoirs, he calls it a white elephant, just to direct the Russians who are spying on the process in the wrong direction. In that case, inside those racetracks here that are shown in that pictures, they had a large number of young ladies there contributing, in that case, to the war effort. Shown here, they call them the uranium girls at the time, basically adjusting the rheostats, the pressure, the resistance of the coils in the magnets. And that gentleman there is working on the coil of a magnet. What is a magnet? A magnet is a coil. Here is a large coil made out of copper that was in short supply during the Second World War. If you get that coil, you circulate a current in it, you get a magnetic field in the center, and that's the shape of those coils right there. Notice then that you needed a bus bar on the top to distribute the electrical power. They didn't have enough copper, so they borrowed from Fort Knox, as you know, that keeps a strategic stockpile of metals and vaccines of the United States. They borrowed the silver from there, and after the war, they returned most of it and replaced it back with copper. You know that silver is a better conductor than uranium. So these were the coils of the calitrons in that case, and the being built. And as you could see, it was a major industrial effort that took the effort of the whole industrial might of the United States at the time. They used 14,700 tons, or about 470 million ounces from the strategic metal silver stockpile at Fort Knox. The site was designated as a White Well site. You can visit it maybe if you drive by Oak Ridge, Tennessee. Another process that, as I suggested, the calitron was a white elephant. It produced gram quantities of uranium to study its nuclear properties, but the real effort went into another process that we'll study later in more detail, which was named gaseous diffusion. In that case, you create molecules of uranium hexafluoride. So that would be UF6. Fluorine is an interesting isotope. I'll send you to the chart of the nuclides. You'll find that in nature, it has only one single isotope. So in that case, if you create uranium hexafluoride as a gas, the uranium 235 hexafluoride isotope would have a different mass than the molecule of the uranium 238 hexafluoride isotope. And in that case, you can create a process of diffusion where you pressurize them and send them through a barrier. Probably it's kept secret until today, but we can guess it may be sintered nickel, because nickel was used later on with steel to resist the corrosion from uranium hexafluoride. Fluorides are very corrosive. And you could see the size of the plant here. It was 1 mile in length of cells that separated that uranium hexafluoride 235 from uranium hexafluoride 238. You could see here the size of it. They called it a mile-long plant. That was designated as a K25 gaseous diffusion plant. That process was very successful. It produced enough uranium 235 for the device that was used on Hiroshima. These are the cells there where that diffusion process was carried out. I'm showing some of the engineers working on it. It gives you the idea of those diffusion cells. Thousands of them were used. Initially, they used mild steel for the material of construction, but corrosion suggested to electroplate them with nickel. And then later on, an alloy of steel and nickel was produced. And this is, and chromium, in fact, and that's what we benefit from today as what we call stainless steel. The nickel formed a layer of oxide on the surface and prevents the corrosion of the material. So a spin-off of the technology there is what we benefit from today as stainless steel. You could see these are the diffusion cells. The gas is pumped with pumps from one cell to the other in a cascading process. You repeat the process thousands of times, and in that case, you can separate uranium 235 from uranium 238. So there we have 3 processes of producing fissile elements, either plutonium 239 or uranium 235. What is left from the process is what we call depleted uranium. And later on, we'll see that depleted uranium had another use and still is continuing to have a use in armaments in general, both as an anti-tank weapon as well as a shielding against other weapon attacks. The uranium hexafluoride is stored in those big, huge stainless steel tanks here being inspected, as you could see. They're sent to the plant in the form of a crystal. When you heat it, it turned into the uranium hexafluoride gas. What you're left with is depleted uranium, also stored, maybe in the future, to be used for a breeder type of a reactor where you use the depleted uranium, which is primarily now uranium 238, absorb a neutron into it, produce plutonium 239, and that would be a form of fission energy maybe in our future. But it also found another interesting application, as I suggested, of anti-tech tank weapons because uranium has a very high density. Consider that the density, if we know the density of water is a standard or the reference 1 gram per cc. If you use lead or silver, in fact, it's 10 gram per cc per centimeter cube, but uranium is 18.9 grams per centimeter cube. So if you have steel that has a density of 8 gram per centimeter cube, and you hit it with a simple small rod or a bullet made out of uranium-238, that's density 18.9, it's like having a saw cutting through wood. So the tank walls, say, made out of steel would be very easily penetrated like a saw cuts wood if you use uranium-238 or what we call the depleted uranium. So we had 2 sites now, one at Hanford, site W, producing plutonium-239. We had site X at Oak Ridge National Lab, producing uranium-235, and they needed to assemble and study how to create a weapon out of those 2 elements. Now, they didn't know, General Leslie Grove and Robert Oppenheimer, which element is going to work. So they basically proceeded in both directions. The site that had to produce the weapon was chosen at Los Alamos in New Mexico. That is still exists today as the Los Alamos National Laboratory, and they designated it as Site W. It was a site of a boarding school in the area that Oppenheimer visited horseback riding. He lived at the University, he lived in California, the University of California, Berkeley, but he chose that site for the scientists that would produce the weapons. Notice here that if you deal with radioactive elements, you have to deal the same way as we deal with viruses and bacteria. So in that case, you get those remote control chambers, or they're called glove boxes because you use gloves here so that you don't touch it with your own skin. And the result was interesting. It was successful. They thought that one or the other process would succeed, but both processes succeeded. On the left side, you could see what a puck or a little flat cylinder of plutonium to the left, held in the hand of one of the technicians there or engineers. And on the other side, that was an enriched uranium ingot. Notice that it is flat because we learn later that if you use a spherical shape, the spherical shape has the least surface to volume ratio of all the geometrical objects. It has a minimum surface to volume ratio, and you can generate a critical mass in the shape of a sphere. Whereas if you flatten it, the surface to volume ratio is less than a sphere, so the leakage of neutrons from the surface is less, so it doesn't create a critical mass. Notice that the radioactivity in that case, in both cases, is very minimal initially. It builds up later on. And these neoprene gloves are really there to keep the materials from getting oil from the hands of the people who manipulate them. So the interesting thing is that both the uranium-235 as well as the plutonium-239 approaches were successful. In that case, they were ready to use them as weapons in that case. At that time, President Roosevelt, who initiated the Manhattan Project, had passed away. He died, and he was followed by President Harry Truman. And the situation changed in that case. And the scientists knew already how much the tremendous amounts of energy that can be released from this type of weapon. A group of scientists started feeling guilty about what we are doing in terms of the possible human life from a weapon made out of plutonium or uranium-235. So there were discussions at the highest level between the scientists and the people in the military and the political intelligentsia, I would call it, about giving the Japanese a warning about the possible use of nuclear weapons. Why the Japanese? Because the Manhattan Project was started by a fear that the Germany would be developing a nuclear weapon. However, the war in Europe ended with the surrender of Germany, so there was no point in using it on Germany after, as Germany had already surrendered. But the war continued in the Pacific region, and Japan was still fighting in the Pacific. And because the scientists know that the destruction can be tremendously large, they suggested that warnings should be made to the Japanese, or some kind of a demonstration to convince them to end the war. So Leo Szilard, who was the one who initiated the whole process with his letter with Albert Einstein, went and found a group of scientists again, that is a declassified letter here, who asked the government, this is a copy of the letter with their signatures, as you could see here. You can read the letter yourself, to give a warning to the Japanese or make a demonstration about the possible use of nuclear weapons. It was debated on a large scale. In fact, some political entities and military entities in the United States suggested that there should be a warning and that there was no need to use the weapons, suggesting that Japan was already negotiating for a surrender or an end of the war, fearing that the Russians would occupy some of the northern islands in Japan. Russia had not entered the war against Japan yet at this time. The debate went on, and the decision was taken to attack Japan. And in that case, it was known that uranium-235 poses no problem in creating a weapon, what's called the gun barrel concept. I'll show it to you in a moment. But plutonium-239 comes mixed up with another isotope of plutonium, plutonium-240. And that one emits neutrons and emits alpha particles. So the people at Los Alamos were not sure that they can build a weapon made out of plutonium-239. The way to do it, they thought, is to create a shock wave at 9 kilometers per second to bring in the plutonium-239 into a very high dense configuration, which we call the supercritical mass. And in that case, they had to test the plutonium weapon. They didn't need to test the uranium-235 weapon. So they came up with the configuration shown here, with a sphere of plutonium core surrounded by a temper, meaning that you have lead or steel or even gold or depleted uranium surrounding the plutonium core, and then surrounded with explosive lenses. How do these lenses work? When you initiate an explosive with an initiator, you create a wave that is diverging. And if you want to compress the core, you want to turn that wave from being a convergent wave from a diverging wave into a convergent, so that the whole thing would be compressed at the center. So in that case, you shape the explosive in what is called explosive lenses. What comes out here as a divergent wave from the initiator turns around and becomes a converging wave compressing the center. So that's a sphere of plutonium now. And at the center, you create an initiator or some kind of a switch. The switch could have been a ping pong ball. On top of it, you leave a little piece of polonium-210. That's the isotope polonium-210. It produces neutrons. At the bottom, you would have a little tiny piece of the element beryllium. When the sphere is compressed, the polonium and the beryllium get in touch with each other. The neutron from polonium interacts with the beryllium, initiating a neutron that starts the chain reaction. So this is a picture from a book, The Curve of Binding Energy, written by Mr. Gamov. I think the book, you can find it at the undergraduate library and you can read about it. This is a picture from the book. That configuration had to be tested. This is another picture of the initiators and the explosives, and then the plutonium core. That would be the plutonium core itself in the center, and this is the spark plug or the initiator at the center. So they had to test the plutonium device. So they built up one of them and they raised it on top of a tower. These are the positions of the initiator. And the test was planned on a location called Alamogordo in the desert of New Mexico. And to test the destructive power, they had to build it above ground. So they built it on top of a tower, and you could see them raising it here. This is the explosive device on top of the tower. This is the electronic equipment that would fire the initiators that start the explosive, and the plutonium core would be right there at the center of the device. You could see that the electronics were very complicated here because all these initiators had to be initiated fully at the same time. So this is a picture on top of the tower there. And if you visit the Museum of Los Alamos, this is a replica of that first device. Robert Oppenheimer was a very literate person, and he knew a lot about Indian mythology, and he named the device or the test the Trinity Test. It became named as a Trinity device, and it's a museum in Albuquerque, New Mexico, where you can see or visit the Los Alamos lab. And history was made the second time after the Chicago Fire #1 and the first explosion of a nuclear device, the Trinity Test. It happened very early in the morning, 4:30 in the morning. And here is the explosion. You notice that it generated a fireball that's about 200 meters in diameter. That's way, way beyond any chemical explosive. The device may have produced not 1,000 ton of TNT or trinitrotoluene explosive. That was about 20 kiloton, 20,000 tons in something the size of a softball. They exploded it at a 100-meter tower, because then in that case, like if you throw a pebble in water, you generate waves, and the waves reflect from the shore. And as they reflect, you get positive reinforcement of a stem wave that would propagate in a horizontal direction. So if you have towers here or any structures, that shock wave would destroy it. This is 0.01 seconds into the explosion. You create a huge fireball because you are ionizing the air, so it emits radiation. And then the air is heated, so its density decreases. So the fireball starts rising up, sucking air from the bottom, and you get the typical mushroom of a nuclear explosion. So as the fireball rises, it creates a vacuum, it sucks the air, and it ends up turning into a toroid, like a large torus, as you could see here. And from the diagram here, as it does that, it sucks the air off the ground. But that air has been irradiated by neutrons, so it becomes radioactive. And as that fireball rises into the atmosphere, the radioactive materials is now spread all over the atmosphere of the Earth, and what we call it is fallout. This happens on July 16, 1945 at 5:29 a.m. in the morning. So the interesting thing is that there was no need to test the uranium-235 device, but there was a need to test the plutonium device. That was the Trinity Test. Now, the United States had a very limited amount of uranium-235, and it was used, unfortunately, on Hiroshima with what we call the gun barrel concept. I'll show it to you in a moment. And the implosion process had to be used on plutonium, and that was on after the Trinity Test. It was used on Nagasaki. Now let's become a little quantitative here rather than qualitative. And study, we said that nuclear energy can produce a tremendous amount of power release. And if we take a single fission event, you'll find that it produces 180 million electron volt of energy. Remember last time we defined the electron volt as the energy carried by an electron when it is accelerated through a potential drop of 1 volt. You'll find that the fission fragments of the fissioning of a single atom of uranium-235 or plutonium-239 produces 165 million electron volts of energy. We get gamma rays, electromagnetic radiation also emitted in the process that gives us 7 million electron volts. These are plus or minus error bars or errors because these are calorimetric kind of experiments. So that's an averaging process. The fission neutrons carry 5 million electron volt of energy. Beta particles or electrons are emitted from the products of the fission itself, which are radioactive. You get 7 million electron volts. Gamma rays are emitted promptly. We call them prompt gamma rays in the fission process, but the radioactive materials resulting from the fission also emits delayed gamma rays at 6 million electron volts. And something very interesting happens when you get beta decay or the emission of negative electrons. For conservation of parity and momentum, you'll find that these are associated with the emission of a particle that's very tiny in size. People debated whether it was a particle or not a particle, but we know now it is a particle. And these particles are what we call anti-neutrinos. Anti-neutrinos do not interact with matter very substantially. They can go all the way through the Earth from one side to the other without interacting, but they carry a significant amount of energy, 10 million electron volt with the emission of the negative electron. So in total, we get 200 million electron volts of energy from the fission process. However, we cannot extract that energy from the antineutrinos. They are in fact a beacon that tells any possible technological civilization in other parts of our universe that there is a civilization here on Earth that has mastered nuclear energy, because they are being emitted right now from all our nuclear reactors when fissions occur and beta particles are emitted. So if we want to think about the energy that goes into the explosive device or into a nuclear reactor, we have to subtract this unavailable neutrino energy. So the 200 million electron volt that generate an efficient process ends up with an unavailable also fission products beta particle and available fission products gamma rays into 180 million electron volt of energy. In the textbooks, you'll find that the textbook tells you that, oh, it's 200 million electron volt of energy, but they ignore that 10 or 5% of that energy, 10 divided in 200, 5% is not available to us. So in that case, if you want to do correct calculation for the power, then you can produce from a nuclear reactor or a nuclear device, it's 180 million electron volt per fission event. Now let's compare that number to the energy we get from chemical processes. If you have an atom of hydrogen and say in a fire, you ionize it, meaning that you get the electron out from the orbit around the nucleus of the hydrogen atom, you spend 13.6 electron volt. This is the ionization energy of the hydrogen atom. 13.6, let's say it's 18 electron volt, and you could see here this is 180 million electron volts. So a single nuclear event produces for you 180 million electron volt, whereas a chemical event produces 13.6 electron volt. This is a tremendously large amount of energy that is contained in the nuclei rather that is contained in the atomic processes. And that tells us really how important the nuclear energy processes that we humans have discovered are to humanity in general. When we measure the energy release from nuclear devices, we compare them to chemical explosives in terms of an explosive that's called trinitrotoluene, TNT. The chemical formula is C7H5N3O6. And if you take one molecule of TNT, you explode the device, it turns into carbon monoxide, hydrogen, nitrogen, and carbon. You get 608,000 joules of energy. And if you do some calculations here, you'll find that in general, if you go to the end of the calculation, that you can produce 1 trillion calories of energy. Another unit of energy, the calorie, is equivalent to 1,000 tons of trinitrotoluene. If you want to use different units, the calories are 2.6, 10 to the 25th power million electron volt, 10 to the 19th ergs, 10 to the 12 joules, 10 to the 6 kilowatt hour, 10 to the 9th BTUs. Engineers have to be able to use all these different units and convert them from one to the other. Look at the different units for energy that we already have considered: the calories, the million electron volt, the ergs, the joules, the kilowatt hours, and the BTUs. 1,000 tons of TNT corresponds to just fissioning 56.8 grams of any fissile material, uranium-235 or plutonium-239. This is equivalent to 2 ounces of material, equivalent to 1,000 tons of trinitrotoluene, or that is basically equivalent to the fissioning of 10 to 23rd fissile nuclei. And we can calculate really how much energy is produced by the fissioning of one molecule of TNT in general. You can read about the distinction between a nuclear reactor and the nuclear explosive, and in the end, the nuclear reactor cannot explode as a nuclear explosive because you have to contain the fission reaction over at least 10 to 100 generations of neutrons. Nuclear reactor accidents will release some energy, but then the system disassembles itself and it cannot produce the energy that you produce from a nuclear explosive. There are technical differences that I describe here, but I want to go for the use, the first use of nuclear energy, unfortunately, in war. Leslie Grove and Oppenheimer had now at their disposal 2 different isotopes that can be used in generating a nuclear weapon, as feared Germany would be doing. With the uranium-235, what you can do is create 2 small hemispheres, 2 small spheres, surround them with a temper, and then in a gun barrel, shoot them against each other. This would be subcritical. It won't generate a self-sustained chain reaction. The other half is subcritical. When you bring them together, and contain them with that temper surrounding them, you would make the system supercritical, and you can release the nuclear energy. What does a temper do if you do not do it yourself, but some crazy people around the 4th of July would have those firecrackers, burn them, and they just explode. If you explode them on the surface of the road, an open surface, they just make a noise and fine, it doesn't hurt anybody. But if you go and explode it in a tin can or a coffee can or in a mailbox, that is criminal, because now the gases are trying to expand, and as they expand, they do work and become extremely destructive. Basically, in demolition engineers, if you watch the Second World War movies, will place their explosives in between the members of the trusses on a bridge to be able to destroy it. Just exploding the explosive on the surface of a bridge will dissipate the energy as a shock wave in the air. So the temper becomes an important part of this nuclear device. Or you can have half a hemisphere in a gun barrel and shoot into it another half hemisphere, and the system becomes supercritical and it starts expanding in the temper and cause lots of, the shock wave causes lots of damage. Or you can have basically a spherical form here and get a chunk shot into it by chemical propellant in a gun barrel. And then in that case, you get a supercritical mass. So this is called the gun barrel concept, and it works fine with in the case of uranium-235. This is the actual device that used a picture of the actual device that was used on Hiroshima. There was no need for testing it in the United States before developing the device. This is a replica of the device, and they called it Little Boy. So the actual design, because you have to arm a weapon before using it for safety, they had really 3 rings of uranium-235. Arming it brought them together, and then they had a gun barrel with a gun propellant shooting a uranium projectile into those 3 rings of uranium-235, which made it supercritical. And you could see the shape here is the shape of a gun barrel. In the case of the plutonium device, they could not use the gun barrel concept, so they used the implosion process. We don't know exactly what was used, but you can have a sphere surrounded by temper, and then you have those explosive lenses that I've shown you before, and you turn it, you compress it, the nuclei come very close together, and fission occurs and energy is released. Or it could be a spherical shell, or it could be even a material that is porous, and you compress it to reach very high concentrations, and the fission reactions would occur. So this is the actual device that was used. That wasn't the Trinity test, obviously, but that was a device using plutonium that was used on 3 days after the first one on the city of Nagasaki in Japan. And they had the name for it, Fat Man. It produced 21 kiloton of TNT equivalent, whereas a Little Boy was less efficient. The gun barrel concept produced only 15 kiloton of TNT. So with a small amount of material, 6.4 kilograms, you produce 21 kiloton of TNT equivalent. But uranium-235 is less efficient. They needed 64 kilograms to produce 1,500 kiloton of TNT equivalent. So definitely plutonium was more, if you want to call it, efficient in the use of material. Modern day weapons primarily use plutonium, but some countries have basically gone the wrong way. They don't know what they're doing, but well, they're just imitating. You find countries like North Korea, Pakistan, as well as Iran, opting for the gun barrel concept, or maybe they should turn it into an implosion process using uranium-235, but it's more economic, as you could see here, to use plutonium rather than 6 kilogram rather than 64, 10 times as much fissile material for the uranium-235 weapons. As I suggested, the United States tested the first plutonium device at Alamogordo, New Mexico. We called it the Trinity Test. There was enough plutonium to be used on Nagasaki, and the uranium-235 that was available was all used. The United States ran out of uranium-235. The Japanese didn't know that. Was all used on the device that was dropped on Hiroshima. So to the left, this is a picture taken of the mushroom from the plane. I think, yeah, it was Enola Gay was the name of a bomber, B-29 bomber that dropped it. Enola Gay was the name of the mother of the pilot of that plane. And that was a little boy here. And then the second bomb 3 days later, from August 6, 1945 to August 9, 1945, the second bomb dropped on Nagasaki. That was a plutonium device, and the pilot named his plane Boxcar. One of them, I think, is at the Smithsonian in Washington, D.C. here. If you can see here on the plane, the B-29 that dropped the Hiroshima bomb, shown here being loaded on the plane, it's called the Enola Gay. And the Boxcar was the one that was used on the for the Hiroshima, for the Nagasaki device. The bomb caused lots of damage because it produced X-rays. These are survivors. That lady here survived, but the X-rays, as you could see, were absorbed by the dark part of the kimono or the dress on the back of that lady. It caused burns. She is a survivor. Otherwise, I wouldn't have shown the picture here. And in that case, the burns were mostly the problem of the survivors. Those who are directly under the weapon, 80,000 of them in Hiroshima, I think, perished. You could see here the destruction at was now named Ground Zero. This is a gentleman there in the middle of the rubble because the X-rays caused fires and burned the whole cities. Concrete buildings were not affected in the same way as other structures that caught fire, and there was no way of fighting those fires. This is a fire engine right here, totally destroyed by the bombing in Hiroshima. You could see how the devastation was in that whole city. And it was, the weapon was exploded 4,000 feet above ground zero and caused quite a bit of damage, as you could see. Concrete buildings were not affected as much as other structures. That particular building there, an observatory or museum, was turned into a museum. This is a picture provided by one gentleman taking the class who visited that what's called the Dome of Peace now memorial. President Barack Obama made a speech there apologizing for the bombing of Hiroshima in general. So this is these are other pictures of the devastations of those weapons. As this is the Hiroshima devastation, some young people foraging there in the rubble. As I suggested, the Fat Man, or the device dropped on Nagasaki, this is the actual device sent by a cruiser, the Indianapolis, to Tinian Island in the Pacific, then taken by that Boxcar B-29, that was the one dropped on Nagasaki. So we are here dealing with the history. Nagasaki had hills around it, so the effects of the explosion was not as significant as the ones on Hiroshima in general. But the devastation was, of course, from the blast effect was quite large. And I'll let you read more detail if you wish about the processes. Notice here we can describe the destruction by different forms of energy release. It can be released in the form of radiation. It can be produced as shock wave and blast. And then the thermal infrared radius, that would be heat that could cause burns and can cause fires, depends on the yield of the device. And if you take the yield to a certain here power ratio, power factor, you can calculate the range of meter from radiation destruction, blast, shockwave, and thermal infrared. You notice that the fireball here in meter affects for a 10 kiloton TNT device, it can reach a size of 200 meters, and the shock blast can reach 1,000 meters or 1 kilometer in size. Nuclear weapons are extremely destructive, as we said, but they were preceded by firebombing of the capital, Tokyo, by using incendiary bombs. And so they used 1,667 tons of TNT conventional devices. And basically, the people killed in the Tokyo bombing was 83,000. And if you think about Hiroshima, 70,000 were killed and 140,000 had long-term effects from radiation. Nagasaki, 36,000. So if you take the casualty per square mile, Tokyo is larger than Hiroshima or Nagasaki, you'll find that the Hiroshima device killed 30,000 people per square mile, the Nagasaki 42,000 per square mile, the conventional bombing of Tokyo was 11,000 at 800 miles. So it's 4 times more destructive than chemical explosives in general. This idea of fire bombing had already happened in Germany on 2 of the German cities, and that led to the surrender of Germany on Hamburg and on Dresden. And this is from the top of the Cathedral of Dresden there. You could see the devastation that happened from the incendiary bombing that was repeated, as I said, on Hamburg as well as on Tokyo. So this is Dresden. This one resulted in much more victims than the nuclear weapons. In fact, 600,000 victims. People went into shelters, but the fire bombing depleted the oxygen in the air. So those people in the shelters basically suffocated to death because of the lack of oxygen. So war is a very, very nasty thing, and we all should think about having people reach some kind of settlement before they go to war. The bombing of Hiroshima and Nagasaki led to the end of the war in the Pacific by the surrender of Japan, but the process continued to a certain degree with the an extra tragedy that happened. What happened was that the components of the weapons were taken to the Tinian Islands in the Pacific by a cruiser. The cruiser was named the Indianapolis, and people who like to call it the Indy. It took part in the invasion of the island of Okinawa in Japan, but it was damaged by a kamikaze attack. It was fixed and then was used to take the components of the weapons to the Tinian Island. It delivered the weapons and was returning back from its mission, but nobody, because they kept the mission so secret, nobody knew in the Navy itself what was the where it was its position. And it was attacked by a Japanese submarine, torpedoed, and it was sunk. And the unfortunate thing is that nobody in the Navy knew where it was. Very unfortunate, and people, the survivor of the torpedoing, were left in the water for 3 days and were later discovered by a reconnaissance plane. But they were subject to attack by sharks, and it was really a nightmare for those survivors. And the story was repeated or in the movie Jaws. If you go to the theater and watch the Jaws movie, you'll find the fishermen describing the ordeal that those survivors went through when they were in the water. And the fisherman apparently was one of those survivors from the sinking of the Indianapolis. They took the captain, they used him as a scapegoat, and they put him on court-martial. He was ordered to go in a zigzag fashion to avoid being destroyed by discovered by Japanese submarines. It was a scapegoat for bad policy. As a matter of fact, The survivors of Indianapolis meet still every year and commemorate the events in Indiana at Indianapolis in the state next to us in Indiana. And the captain was later on basically 32 years after he committed suicide because he was so upset. He was absolved of the charge of negligence by an act of the United States Congress, cleared his name at the request of his own sailors. The captain of the submarine, the Japanese submarine certified basically that he could not, his exact pattern would not save the situation. The submarine was a Japanese submarine, I-58, under Lieutenant Commander Mochichura Hashimoto. And the submarine has not scored any hits since the beginning of the war, but he testified that it could not have changed the situation. So that was another tragedy that happened there, and the war with Germany and with Japan, and today in the Ukraine with Russia, are simply same parts of history. But an interesting part of the discussion is that there are still historians that are disputing the need for using the atomic bombs on Japan, because Japan already was trying to find ways of ending the war, fearing that the Russians will join the war, and they had their eyes on some of the northern Japanese islands. This is pictures of Mr. Oppenheimer and General Leslie Grove after the Trinity explosion. You could see that is what's left from the tower. It totally vaporized, and it tells you about how destructive those atomic devices can be. At the location of the tower now, there is a monument designated as a Trinity site, and it's a historical site open to the public once a year in the first Saturday of the month of October. So if you are there, you may be able to get and visit it. So if you have, say, an internship with the Los Alamos National Lab. In fact, one of the students in our class right here was assigned to a nearby as a project manager for a nearby Air Force base, and he visited the site on that date, and he sent us a picture of himself standing by the monument. We would like it to be part of history that nuclear weapons are not used ever again by humans. And I'll conclude the lecture today along this line, but invite you to look at some of the appendices about the milestone, more detail about the milestones that led to the situation that we have today in nuclear energy. And I also included some materials about the discussion that would last forever on whether the nuclear weapons should or shouldn't have been used by the United States to end the war with Japan in the Pacific. And the arguments are very, very, very contentious. This is the transcript of President Barack Obama's speech in Hiroshima, Japan, as reported by the New York Times, where the United States basically, now Japan is a good friend of the United States, when it was at a very destructive war in the Second World War. So this is a transcript of President Obama's speech, practically apologizing for the bombing of Japan, nuclear bombing of Japan. Admiral Isoroku Yamamoto, a Japanese admiral, he was educated in the United States, And basically, a very famous quote is that I fear all we have done is to awaken a sleeping giant and fill him with a terrible resource, describing the war of Japan with the United States. President Harry Truman had to take the decision of the bombing of Hiroshima, but the Secretary of State Stimson, for instance, was opposing it. Many people opposed it. Historians are still debating it. General Douglas MacArthur also concurred. General Eisenhower, who became President Eisenhower, also concurred that there was no need for the bombing of Hiroshima, but some other people come with the opinion that it was needed to end the war, to save both military lives on both the Japanese and the Americans, as well as to save civilians on the Japanese side. So the history would continue forever. And this is another appendix on the information war in the Pacific in 1945 that you can read or not read. But what I'm going to do is give you an assignment where you access a chart of the nuclides to learn more about the war, the isotopes in general. All right, I'll stop sharing here and open up the chat room for anybody who would like to ask questions. And please access the assignment and to learn more. And please read the material, because I cannot cover everything in the lecture notes. So our lecture stops at this, and I'm open for any questions in the chat room.